Hello everyone, good evening. Welcome to the course of Defects in Crystalline Solids Part 1. This is an NPTEL 8-week course where you will be introduced to crystalline solids, the defects in crystalline solids, and how these defects affect the properties in the crystalline solids. The course coordinator for this course is Professor Shashank Shekhar from IIT Kanpur, and I will be the teaching assistant for this course. Regarding the doubts for this course, you can always ask the doubts in the discussion forums, which is provided by NPTEL, or we can discuss your doubts. If you want a live session discussion, if you want to clear a doubts one-to-one, we can discuss it in these problem solving sessions, which I will be taking care of. But if still on my half I am not able to clarify your doubts, we can always refer to Professor Shashank's notes or Professor Shashank himself to help us with our doubts. So yeah, let's begin the course. Just to give you a brief idea about what we learned in the previous session. In previous, we began this course with learning about crystallinity. Then we discussed about the defects in the crystalline solids. Then when we classified the defects into various types based on their dimensionality: 0 dimension, 1 dimension, 2 dimension, and 3 dimension. We discussed a lot of information about zero dimensional defects, how they are present, how they are formed, or how they are transferred, how they jump from one place to another. We discussed about their movement also from zero dimensional defects. We discussed extensively about these zero dimensional defects. In the previous few sessions, we have started one dimensional defects. Those are dislocations and disclinations. We learned about the difference between dislocation and disclination from the Volterra model. Then we differentiated, we concluded from the Volterra model that disclinations are very rare in case of the metals we are considering in our general use. Dislocations are quite common in the metals. So we'll be focusing our discussion mostly on dislocations. Then finally, we discussed to a great extent what are the types of dislocations, such as screw dislocation, edge dislocation, how are they occurring. If you want to see some videos of screw and edge dislocations, you can always refer back to the previous sessions which I took, where I showed you the video of how the screw and the edge dislocation looks like. Then we have edge dislocation, we have screw dislocation. We discussed about their interactions, how they are interacting with each other. If a screw is interacting with edge, if a edge is interacting with edge, if a screw is interacting with screw, what type of changes takes place. Even in the lecture, Professor Shashank solved some problems regarding these two questions, like dislocation interactions. How are they interacting? How the screw is interacting with screw? How the screw is interacting with edge and all. Then finally, we discussed about image forces. What is the definition of image forces? In image forces are those forces on the dislocations present at the surface which will be removed out from the surface. That means the surface of a material is always dislocation free, because if there is a dislocation present at certain small distance from the surface, it will always try to get out of the surface. It will always try to move out of the surface, move out of the material. So it by explanation it is explained that there is a oppositely kept force dislocation outside the material, or mirrored dislocation outside the material, which helps in annihilating or brings this attracts the dislocation out from the crystal. This is what image forces discussed about. So from this thing we understand that if a material goes to the nanoscale, if the material is too small in the nanoscale, so as the surface area of nanoscale is too large, all the dislocations present in the surface of the atoms go away. So the materials in the nanoscales are almost dislocation free. And coming to the theoretical strength, remember theoretical, where we began the definition of defects. Remember about theoretical strength, right? What does the theoretical strength? What is the theoretical strength of steel? It's around GPa, 8 GPa, right? That means if we do not consider dislocations or any defects in the material, the strength of the material can be in terms of gigapascal. So, when we consider this the presence of defects such as dislocations in the material, then the normal what is the the yield strength which we are observing is decreased because of that. That's why the theoretical strength is not valid because of the presence of sorry, because of the presence of defects in the material. So when we are going to the nanoscale region, we are saying that the material will be defect free because of these image forces. What does that mean? If the material is defect free, the strength will be extremely high. That's why you can see extremely high strength at the in the nano viscous, which is present in the nanoscale, because there are no surface defects present in the sample. This was what we discussed in the previous sessions. We solved some problems regarding the sessions, and I think most of the questions in the assignments are also solved from discussing these portions um in the previous sessions. In today's session, we'll be focused mainly on the motion of dislocations, how the dislocations move. Dislocations will not stay in one place, they will move. As I showed you in the previous videos, they will move. But how the dislocation movement takes place, this will be discussed in this few weeks. Let's have a look. The motion of dislocations, as explained by Professor Shashank, occurs by two things. One is glide, one is climb. What is glide? Glide, as you know, there will be a movement of dislocation along a plane. There is a plane in which the dislocations will be present or in which the Butcher vector will be present. So the movement of the dislocation is along that plane or on that plane, which contains both the Berger vector and the line vector. If there is a moment of dislocation, what is that called? That is called glide. As you can see here in this figure, as you can see here, glide. Let's see glide. This is an H dislocation as there is a half plane present here, the extra half plane present here, where the bonding there is no bonding in the other half plane. Only a single half plane is present. So when we are saying it is moving along this direction, there is a dislocation line here. This is the dislocation line where the Berger vectors is in this direction. This is the Berger vector direction. So when we are saying it is gliding, so there should be a plane where the line vector and the Berger vector are in the same plane, and in that plane there will be a movement of atoms. So as you can see here, this is the plane we're talking about. There is a movement of atoms. There is a creation of new bond, and this the dislocation is shifting, jumping from here to here, from here to here, from here to here. It jumps around. This is known as a glide. Similarly, for screw dislocations, you can observe the glide as you can see here. Screw dislocations, as we know, there is a rotation. There is a rotation among in the lattices, and you can see here this rotation is taking place here. How is the movement happening? You can see here along a plane which contains both B and U. There is another term. This is one way of motion of dislocation. Then another way of motion of dislocation is dislocation climb. So climb, as the name suggests, what do you understand by the term climb? What is happening? The dislocation is climbing. That means climb. So what? Think about the edge dislocation. Let's come to the edge dislocation once again here. What is happening? There is a dislocation here. The dislocation moves up. This half plane moves up. That is known as the dislocation climb. It moves up. Similarly, there is screw dislocation. What is a cross slip situation here? How does a cross slip occur? It will be shifting. There will be a shifting of atoms, as you can see here, upwards. That's known as a climb. So we know that the dislocation. So what is the difference between a glide and a climb? As I told you, glide happens in a plane where the dislocation line and the Butcher vector are in the same plane, containing the same surface of the same plane. But in climb, the dislocation move out of the glide plane. The glide plane is there, but the dislocation is moving out of the glide plane. It is moving to up or somewhere else, out of the glide plane. One point I told you earlier is that in glide, the dislocation line and the glide plane contains the dislocation line as well as the Berger vector. So as the climb happens away from the dislocation out of the glide plane, that means it will go perpendicular to the glide plane. It is not present in the glide plane. The movement of the dislocation is perpendicular to the glide plane in case of a climb. Another point to note here is that what we know about edge dislocation. In edge dislocation, what is happening? The line vector is always perpendicular to the Butcher vector in case of edge dislocation, whereas in case of screw dislocation, the line vector is parallel or anti-parallel to the Butcher vector. So that means in edge dislocation, there is only a single plane in which glide will take place, because in glide plane should contain both u and b, and u and b will be perpendicular in a single plane in case of edge dislocation, and that will be the single glide plane in case of edge dislocations. But in case of screw dislocation, the U and B are always in line with each other, or are always parallel or anti-parallel to each other. So they will always lie in the plane. So that means multiple planes are present in case of multiple glide planes are present in case of screw dislocations. Did you understand the concept what I'm trying to say? This is what it is. And another point to note here is the difference between glide and climb. The glide, as you can see here, it's quite simple, right? Like there is movement of atoms, this is movement of this is happening. But what happens in climb? You need to create a vacancy. The atomic movement, there should be an atomic movement upwards. You need to substitute something, so it requires more energy, the climb one. So which do you think the crystal will prefer, glide or climb? That's the question which stays. Let's discuss it afterwards. So now we know that there are two methods of dislocations. One is glide and one is climb. Let's watch a video like to how the how the glide takes place in the real crystal, which is taken from a live TEM video. Let's see what is happening in that. Let me show you how the dislocation movement happens in case of this motion of dislocation happens. These are dislocation lines. Oh my god. Just a second. Oh, okay. Only for it is available. Okay. See, these are the dislocations. How are they moving? You can see how are the dislocations moving. This is a glide plane. They're moving along the glide. See, the dislocations are gliding. It looks so nice. They're entangling, then they are gliding again. Yeah. So this is what dislocation glide is. But one more point to note here is that, do you think the motion will be much easier? As I told you, okay, in a plane, there is a plane, the dislocations will move across the plane. Climb, the dislocation will move perpendicular to the glide plane. Do you think it's that easy? No. There will be a resistance to this dislocation, a movement of dislocation. There is always a resistance to the moment of dislocation. So what is the resistance to the moment of dislocation? What is resistance to the moment of dislocation? The width of the core and the lattice resistance. These are the these are the things which resist the moment of dislocations. Before discussing this, let's solve a question on the basis of line vector and Budger vector and edge and screw dislocation. This is a very simple question. Like to, if you have understood, sorry, like if you have understood um, what is going on in edge and screw, this is very easy question to answer. Let me solve it for you. Let's see the question. What is happening? Determine the following dislocation as edge, screw, or mixed. Identify the slip plane in which the dislocation lies. Simple question, right? Sodium chloride slips on the 100 slip system. Fine. So we have to identify the edge, screw, or mixed. How can you identify if it is edge, screw, or mixed? You know that in edge, screw, and mixed. Let's differentiate. How can it? In edge dislocation, the Berger vector is always perpendicular to the line vector. I'm talking about vectors. Berger vector is always perpendicular to the line vector. In screw dislocation, Berger vector is either parallel or anti-parallel to the line vector. Parallel or anti-parallel to the line vector. And in mixed, what Professor Shashank discussed, like this is perpendicular, so the angle between them is 90 degree. This is parallel, the angle between them is 0 degree or 180 degree. Both are almost same because you're taking a different side. Anti-parallel, if it is anti-parallel, it's 180 degree. If it is parallel, it's 0 degree, but the value is almost the same, the magnitude is same, right? So what is mixed dislocation? What happens in mixed dislocations? If the angle between Berger vector and line vector is an acute angle. Acute. What is acute? Acute angle is the angle lying between 0 to 90 degree. So if any value of angle lying between 0 to 90 degree is present in case of a slip system, then this is known as a mixed dislocation. Did you understand what I'm trying to say? So how can you identify edge, screw, and mixed? We have to take the dot product between B and L so that we can know if it is perpendicular. We can find the angle from the dot product, right? So let's do B dot L for A. So how can we do B dot L? 110 B dot 1 bar 0 B dot L. How can you do the dot product? Do you remember? Multiply A into A, 1 into 1, minus 1 will be minus 1, plus 1 into minus 1 will be minus 1, plus 0 into 0 will be 0, divided by what? 1 square plus 1 square plus 0 square. 1 square plus 1 square is how much? Root 2, right? Multiplied by 1 square. This is just I'm doing the dot product. Multiplied by this square, 1 square plus 1 square minus 1 square plus minus 1 square plus 0 square, it will be same root 2. Got it? Then solving this, you will get minus 2 by 2 or equals to minus 1. So what does the cost dot product give? Dot product gives the value of cos theta, right? So cos theta is equal to minus 1. What is theta? 180 degree, anti-parallel, right? Anti-parallel. So anti-parallel, it is anti-parallel. That means what do we know? If it is parallel or anti-parallel, it will be a screw. So this is a screw dislocation. Similarly, let's see about this problem. What is saying 0, 0, 1, 0, B, 0, 0, 1 dot 1 bar 1, 0. Let's take the dot product. Cos theta equals to, what is the value? 0 into minus 1, 0, 0 into 1, 0, 1 into 0, 0. 0 divided by anything. 1 into 2. 0 divided by anything will be 0, right? So cos theta equals to 0. So what is theta? Theta equals to 90 degree. Cos 90 equals to 0. So where it is 90 degree, where B is perpendicular to L, this is 90 degree. So this will be H dislocation, right? Then comes point C. Let's see what is happening in C. 1, 0, 0, 1, 1, 1. Let's find the value of cos theta. 1 into 1, 1 plus 1, 0 into 1, 0 plus 0 into 1, 0. 1 divided by 1 square plus 0 square plus 0 square is equal to root 1, which is equal to 1 into 1 square plus 1 square plus 1 square root over is equal to root 3. So cos theta equals to 1 by root 3. Right? Did I do anything mistake? Right? Cos theta equals to 1 by root 3 we are getting. So when is cos theta equals to 1 by root 3? So when cos theta equals to 1 by root 3 when theta is between 0 degree to 90 degree. Remember, right? Cos theta 60 degree or 30 degree cos theta value will be 1 by root 3. So the theta value is 0 to 90 degree. That means it is an acute. That means it is an mixed dislocation. So the third one will be a mixed dislocation. So number A will be screw, number B will be H, and number C will be mixed dislocation. You understood what is going on right now? Yeah, let's move on to the concept. Like as I told you, the dislocation moment of dislocation does not happen so easily. There will be some resistance which will be existing to the motion of dislocations, and this resistance arises due to the width of the core. We discussed about the width of the core before, like it is 10% of the total Berger vector, or b by 10 is the width taken generally for approximation. So what does this mean? In the width of the core, the linear value of equations is not valid, or linear elasticity is not valid in the width of the core. Linear equations are not valid in the width. Away from the width, all the linear equations and derivations are all valid. But within the width of the core, it's not valid. And it was seen that the width of the core is different for materials to material. It will not be same for all the materials. It will be different from every material. So that means if the width of the core is different, there will be a difference in case of resistance to dislocations movement for different material because the width is different, and we said that the resistance it affects the resistance of the dislocation moment. And it was found that if the width is wider, if the material has a wider width, the movement of dislocations will be easier rather than a material having a narrow width. So in width, if a wider width, in a wider width, the dislocation movement is easier, wider width, than the narrower width. In wider width, it's easier than the narrower width. Then another point is lattice resistance. What is lattice resistance? Let me explain you. This is, let's suppose this is an edge dislocation. I'm drawing an edge dislocation. This is an edge dislocation, right? This is the edge dislocation. Sorry, let me just eraser. Yeah, this is the edge dislocation, right? These are all atomic points. So what is happening here? In edge dislocation, we said the bond, there is an extra half plane, a dangling plane, right? There is an atom here. This is a dangling atom. This has no bonds within. So what happens in how does the movement happens in case of an edge dislocation? I showed you the atoms which is present here will try to create a new bond here. So this plane will become the half plane. Like that, it will move towards the other planes. So the final stage, what is the this is the initial stage. What will be the final stage? The material will look like this. There is a new bond created. There will be a bond missing here. There will be other type of atoms present. This is the final stage. But within this stage, let me show you something. Within this stage, okay, these are the material. This is this. This is one breaking of bond. This. So within this stage, what is happening? The bond which is present with the bond which is present with this is breaking off, and the new bond is created with this atom, right? So there will be a stage when the atom is within this. There will be a infinitesimally small amount of time where the atoms will be this in this region. This is the region of high energy because the atoms are not stable, because the bonds are not present. There is a dangling bond within the material. That means the atoms are not stable. So this is the point where the stability is minimum. And this requires higher resistance to for the this creates higher resistance to the moment of dislocation because the stress required will be higher. This was explained by Paul Navarro, and they gave the value which is known as the Paul Navarro stress, which is equivalent to 2g by 1 minus mu exponential minus 2 pi gamma by b, as explained by Professor Shashank. Right. So the dislocation or the movement or resistance to the motion of dislocation depends on two factors. One is the width of the core and one is the lattice resistance. So what do you get from these things? What do you understand from these things? As we said, wider the wider the width of the width, the movement will be that much easier. And the lattice resistance when it is two denser planes, that means if the interplanar spacing is higher, if the interplanar spacing is in the material is higher, the movement will be easier. That means denser planes show slip of dislocations. So the Berger vector present should be too small along the direction with the shortest distance translations. That the, uh, the shortest distance translations is the, what is that? Is the close back direction. Close back direction is the shortest. In case of a BCC, it's the body diagonal. In case of an FCC, it's the phase diagonal, which is the shortest path. Then we discussed about the slip systems present in FCC, BCC. We compared what can be called as the slip system. Why is it called as the slip system? There are two things we noted. In a slip system, in a slip system means what? There is movement of easy movement of dislocations. So easy movement of dislocations means the resistance is minimum and the width is maximum. Width of the core is maximum. That means a slip system should have a larger distance between the planes or larger interatomic planes so that the width of the core is smaller, wider. And then the lattice resistance should be minimum. Lattice resistance should be minimum with P should be less. B is less. That means the largest atomic density planes is the plane with B less. So the slip system is defined as the sample system where the largest distance between the planes is taken into account and largest atomic plane density is taken into account. If these 2 points are taken into account, that's the maximum, the value we get, the maximum or the minimum value we are getting is defined as the slip system of that unit cell. Like FCC, what is the slip system? 111 plane, 110 direction is the slip system. How to find out the values of atomic density and everything, Professor Shashank explained that. You can always go back to his notes to check into that. Then there is BCC. And in BCC, we observed that 110 plane, 111 direction, 112 plane, 111 direction, and 123 plane and 111 direction. These are the various directions where the movement of dislocation is easier. Multiple slip systems in case of BCC, whereas in case of FCC, there is only one slip system. Then we'll solve various problems regarding dislocation density, etc. We'll solve various problems regarding dislocation density and all. If you have any doubts regarding this problem, we can always discuss it in the class. Feel free to ask me in the class, or I can solve them in the class if you want. If you have some doubts still. Then finally, we discussed about resolved shear stress. Right? What is that? What is that? Then there is a critical value of resolved shear stress. What is that? This concept arises when we apply a load to a material. As you can see here, we are applying a load to a material and we are calculating the stress on this material, on this plane, and this stress will give you resolved shear stress on the plane. And if the resolved shear stress value is greater than some standard value, then the material will slip along that plane, or the moment of dislocation will be along that plane, easier along that plane. And that critical stress above which the plasticity happens, or plastic deformation happens, is known as critical resolved shear stress. That is the minimum value of strength or stress above which plastic deformation takes place. That's why it's known as critical resolved shear stress. And critical resolved shear stress is defined from the formula sigma cos phi 1 cos phi 2. This is resolved shear stress. And if you are finding critical resolved shear stress, this is a material property. it will be constant for a material, because after this stress the material yielding starts. So this will be a material property, not the property we got from the formula. The formula gives us the value of resolved shear stress. What is the value of shear stress, resolved shear stress? But the value of critical shear stress is a de- predetermined value, above which plastic deformation or the yielding occurs. So there was a question in the assignment like which of the statement is not true about the critically resolved shear stress? Let's see. As I told you, it's a material property. So CRSS is a material property. This is the right thing. Then CRSS is a resolved shear stress at which yielding begins inside the crystal, marked as a onset of plastic deformation. This was also I explained, beyond which the plastic deformation takes place. Then another point we discussed here is that the CRSS is a material property, right? So it does not depend upon the applied load, whatever you are applying. This is the same in case of elasticity. Let's talk about the Young's modulus. What happens in Young's modulus? It is a material constant. It does not depend on anything else. It is a materials constant. Young's modulus, right? So similarly, CRSS value is also a material constant. For material, it is predefined. So it does not depend upon the apply load, right? It does not depend upon the apply load. Does not depend upon the apply load. Then CRSS does not depend upon the crystal orientation. This is true. It depends on the crystal orientation. We have to see how the crystal is oriented. We are finding the schematic factor or angle. Cos phi and cos phi 2 depends on the direction. Of course, the orientation is important. So this is the one which is as not true. So this is not true for CRSS. Does not depend upon the crystal orientation. Does it depend upon the crystal orientation? How the crystals are oriented? Sorry, I by mistake forgot about. I by mistake. My mistake. I told you that it depends. It does not depend upon the crystal orientation. Of course, it does not depend upon the crystal orientation. May it be crystal oriented along 1, 1, and 0. We just need a value of this. So to find out on which slip system, which is the slip system of the material, or on which the slip happens easily. It does not depend upon in which crystal is oriented. If crystal is oriented in some other direction, the slip will occur in that direction. But we need to find out which crosses the CRSS value, the value of the slip system which crosses the CRSS value. So this is the only correct answer. CRSS depends on the load. It does not depend upon the load. Yeah. So this CRSS condition of the CRSS concept is valid for a single crystal. We are considering this material as a single crystal, and then we are finding the schematic factor or the CRSS value, critical resolved shear stress value. But in real life situations, we never deal with single crystal. It's very difficult to produce a single crystal material. Nowadays, though, due to the advancement in various engineering techniques, we are able to produce single crystal materials. But generally speaking, all the materials present are polycrystalline materials. That means there will be a large number of crystals in case of a polycrystalline material. So in a polycrystalline material, if I am applying a stress in a polycrystalline material, large number of grains are present. If I'm applying stress in a polycrystalline materials, and we think that all the single crystals present in a polycrystalline material slip along a particular direction. Right. Let's suppose that they are slipping along a particular direction. What will happen? They are oriented in a polycrystalline material. They are oriented in a different way, So if the slips happens in a particular direction, then in the other grain it will happen in the other direction because the orientation is different. That means there will be a tension between in the interface between these two grains. There will be breaking or porosity, or there will be some kind of gaps arising in between these grain boundaries. This is not true. Actually, this does not happen. When you are applying force immediately, they does not they did not get break through the what we call they do not get break through the grid boundaries. So that means a slip system must be multiple. It should have multiple slip system so that if one plane in this slip occurs, in the other plane the slip will occur in the other direction, so that the grains morphology will remain intact. So to ensure contiguity in the deformations, we end up getting five independent slip systems in case of 3D samples. We require five independent slip systems for the sample to keep homogenized or contiguity in the deformation. Then we discussed about glides, like how they happen and how their movement of glides occurs. Glide movement occurs with the help of kinks. There is no easy movement of glide. Okay, we think okay, the dislocation, let the dislocation will be moving. No, the glide dislocation, there is a gliding of dislocations with the help of formation of kinks. And kinks, as Professor Shashank explained about, kinks are little thing and how they are oriented along the line vectors and how the budget vectors are taken into account. So we finally got that the movement of kinks leads to the movement of glide, which leads to the formation of dislocations, a movement of dislocations. Right. So the movement of kinks finally conclude is the movement of dislocations, because movement of kinks helps in glide and helps in the formation, finally helps in the formation of dislocations. This was about what Professor Shashank discussed in this week, and there are various problems related to this week. I think most of the formulas and everything are covered, and the problems are quite easy. And some of these problems are solved by Professor Shashank in his lectures as well. So you can always go through that. But if you still have doubts, we can always discuss it in the this class or in the discussion forum. This was all about today. Thank you so much.